for your test, we're going to do those during our lab session, as always. Overall, I thought the grades were pretty good. And for Eco Club, this Friday from 9 to 12, I've got a little flyer up here for you guys. We're going to be doing our trail cleanup. In the past, if you look at all of our Eco Club activities, they tend to be an hour long. Because this is 3 hours long, what I've decided to do is that every hour that you work will count towards those 5 points. So in the past, if you looked on there, it said, for 10 points, you need to do 2 activities. Well, the equivalent of that is 2 hours. So if you come work for 2 hours, that's 10 points. And that will cover that spread if you're trying to get some extra credit, okay? So that'll be Friday from 9 to 12, but they're going to be doing sign-up starting at 8:30, from 8:30 to 9 o'clock, because at 9 we actually get started in the trails. We knocked out a lot of it during our big service day, but we still have one path of the trail that needs quite a bit of work, and then the new trail that we started around the backside definitely needs a lot of work.
Where is it?
It is going to be across from the Vet Tech building.
Okay.
Do you know where that is?
No.
No? You know what tennis courts are?
Yeah.
Okay, it's on the opposite side of those, across the drive that comes in.
Okay.
Yeah, so if you just park next to the tennis courts, you'll see us out there, and there'll be a sign-up sheet and all this stuff. But I'll remind you as as that day gets closer. Okay. Sorry, I'm getting a little sick here. Stay back. I know, right? That's why I'm over here. All right, so we're moving on to our ecology unit, and our ecology unit is one of my favorites because that's really where I did a lot of my research as a grad student along with insects. But in terms of ecology, we've been mentioning things from the very beginning of class, from our plant unit, our produce unit, into our animal unit about evolution and adaptation. And one of the things we looked at in the video last time was kind of this predator-prey. And the idea that it's these external factors that are driving animal adaptation, okay? Or it's driving plant adaptation. And ecology really kind of solidifies that idea because it really pulls everything together in terms of how evolutionary adaptations occur throughout all of your plant and animal groups. Okay? Because it's those relationships, those pressures, not only from the environment, okay, in terms of your abiotic factors, but also from other species. Okay? So it's these guys that are interacting with one another that's causing these shifts. Okay? And one of the big ones that I really enjoy is behavioral ecology, because behavior definitely affects fitness of your organisms, okay, their survivability and reproduction. So in this chapter, we're going to look at some of those behaviors with animals, in that we're going to look at the difference between innate behavior and learning. Okay? Innate behavior is that instinct. Okay? We're going to identify approximate ultimate causation, and this is what animal behavioralists are really asking in the big question. Different types of learning, for example, the different types of associative learning that we're going to be dealing with, how animals are able to communicate, and of course, the behaviors on the behaviors, how they affect their fitness, right? So we talked about that a little bit before. For example, we talked about very early on how parental care plays a big role. That those organisms that do provide parental care, you see that there's a greater chance of survival for their offspring versus those that don't. Okay, and we even mentioned that whenever we were talking about some of our animals. Now, as we were just saying, I do put a stipulation on this. I will use humans kind of as an example in terms of how we do this to do this. Animal behavior doesn't necessarily translate to human behavior. We are a way more complex species. We really kind of make judgment calls. We all have different behaviors. But kind of some of the underlying behaviors, for those of you that have taken psychology, you'll probably see there's a lot of very similar things that we see in animal behavior that do, at least in part, translate to kind of us as a species, whether it be a primate or a humans. But it does get way more complex. So if you find this really interesting, that's where you should probably go, is look at animal behavior, go look at kind of human behavior, because there definitely are a lot of differences. You can't use the things that we learn about here to explain the human condition. Okay? As easy it may seem to be, it's not quite that easy. Okay, so what are we dealing with in behavioral ecology? Okay, what you're looking at is you're trying to look at animal behavior by studying how behavior is controlled, how it develops, how it evolves, and how it contributes to your fitness. So again, we're looking at this in the big picture. We're looking at, okay, we've got organisms, there's a wide variety of genetics in there in order to look at, say, fitness. But it's not just their survivability or reproductive success. You're also looking at how their behavior contributes to that as well. And that should make sense. If you have a very risky squirrel that goes and plays in traffic all day long, what's its chances of survival? To go play in traffic? It's going to survive long?
Oh, survival, yeah,
No, not so good, right? That's a risky behavior. So those organisms that follow risky behavior probably will not survive long enough in order to pass on any of those behavioral traits, okay? So we're going to break this down, and we're going to make this a little bit more simpler to look at, because we're going to break it up in terms of proximate and ultimate causation, okay? Because an animal behavioralist is asking those big questions, but really you can sum it up as to how and why. Okay, so somebody like Jane Goodall, who was studying primates, you would go and you would ask, okay, well, how is this behavior working within this, say, family of primates? And then the big question is, well, why is it working? How does this contribute to their fitness? Okay? So whenever you look at the how, you're looking at what is called the proximate causation. Okay? Proximate, like proximity being close. Okay, the proximate causation is how this behavior actually works. Okay? And in this case, you can look at it from a couple different standpoints. Is it something that is hormonal? Okay? Is this controlled and regulated by your internal system? We do this all the time. You know, the sun comes up. We are on this circadian rhythm that we get up and we go to bed relatively, I say relatively, around the same time every night. Hopefully you do, right? Everybody gets good sleep. Or is it something that's more neural? Is it something that is more that you see something, right? So if you respond to someone attacking you, we kind of have this fight or flight mechanism in place, right? Where you're able to make that judgment call because you're receiving all these external stimuli and your brain processes those, okay? That's the how, okay, how this thing is working. And most of the times the way that we see a lot of these behaviors is that stimulus is coming from that external environment, okay? The way that we react to things, you know, if you're driving down the highway and see a car swerve into your lane, you're going to react. That is a behavior, a survival behavior, right? You want to live, so you will swerve or you will take necessary steps, okay? That stimulus is from the external. The ultimate causation, though, is the big question as to why. What is the purpose of that behavior, and how did that behavior evolve, okay? So the easy way to look at it is, how does this behavior contribute to fitness? Okay? How does it contribute to your survivability? And how does it contribute to your reproductive success? Okay? To put it in a different framework, if we look at the behavior, the proximate, the ultimate, these are little stickleback fish. The males have a red underbelly during your mating season. And what you find is that the behavior here is that a male stickleback fish will attack other male sticklebacks that invade its nesting territory. So if you look along this, they kind of drew a little line here trying to state, okay, this is his nesting territory, and this guy's getting awfully close to getting it into his territory. So if you were watching, say, this fish tank, you would see one begin to become very aggressive or attacking the other one. The proximate cause, how this is working, is that it's actually the red belly of this male that acts as that external stimulus that causes aggression in this other male. And they've done some pretty neat studies with this. They made some little bitty wooden, little bitty sticklebacks that they didn't paint the bottom. There was no aggression, and that made sense because the females don't have any red underneath the bottom either. But they went ahead and they made round objects with just the bottom red. It would attack it. They made triangular objects and stuck it in there with the red bottom, and it still attacked it. It was that condition of red, particularly on the bottom, that elicited this reaction. There was even a kind of this anecdotal story that I read in which there would be a red vehicle that would drive by, and the fish tank was near the window, and every time this truck would drive by, this one fish would get extremely upset and try to attack that truck through the glass, even though it's out, it's driving at the light. This thing would literally see red and get very, very aggressive towards it. But the ultimate causation, why this behavior would continue, how it contributes to survivability and reproduction, is that by chasing away other males, you decrease the chance that those eggs in your territory are going to be fertilized by somebody else other than you. Okay? So let's kind of take this as an example. Let's pretend that we have a whole group of these males, and you have males that are very aggressive versus those that are not aggressive. Okay? If you have that kind of situation set up that you have a lot of variation in terms of aggressiveness, okay, what's going to happen to those males that are not very aggressive? What's going to happen to their territories? They're not going to fertilize as many eggs, are they? Because the other aggressive males will take over their nesting territories. So what does that mean for the offspring of that next generation?
More aggressive.
They're also going to be more aggressive. All right. So within a few short generations, you'll find that non-aggressiveness is essentially gone because it doesn't increase your fitness. It's only the aggressiveness that increases your fitness. Okay. Now again, this gets into some genetic aspects of it that we're going to talk about in just a second. But you can see how very quickly that this can occur, because if you're not guarding your eggs, you're not going to get to reproduce with them. Okay? You're not going to be able to spawn with those females because you can't hold your own territory. That is an indication that your fitness is low versus all these other males that have a high aggressiveness that they increase, okay, their fitness. Okay, so the proximate cause are those that focus on the immediate stimulus and the mechanism for the behavior. So in the last one, we're looking at the stimulus, of course, was that red belly. The mechanism for the behavior, okay, that was a sign stimulus. It was an external. Okay, it wasn't hormonal. It wasn't something that happens once a year, like estrus or reproduction or something along those lines. The ultimate cause is looking at how it contributes to fitness, which is survivability and reproduction. Okay? Now, because we're dealing with behavior, we're essentially going to be talking about learning. Okay? Learning. Learning is simply the modification of a behavior based on experience. So whenever you say birds learn, you're being truthful, right? When you say that, we can even go down to amphibians learn. Well, of course they're learning. They're modifying their behavior. Some people like to take that term kind of to the nth degree, and it's like, oh, only humans can learn things. Well, no, that's not true. We know that. Dogs learn things all the time. Keep going down the line. Cephalopods, they learn things as well, okay, as we're going to see today in lab. So many, many animals have to learn, and that should make sense. They have to learn what foods they can eat and which foods they cannot eat. I learned something yesterday. Dogs can't eat grapes. It will kill them. I did not know that. So I'm still learning. There's just something in there that toxic to them, but not to us. It's kind of like chocolate. So don't feed your dog grapes. I didn't do my dog's grapes.
My dogs.
I just read a list. I was like, oh, that's on a list of things. I come across the most random things ever. So I learned. Now I'm modifying my behavior.
My dog beat the odds then.
Well, that's good.
Yeah.
Most of our examples of learning comes from birds and mammals. We will talk about more in lab today, of course, because there are other examples of that, like I said, cephalopods. Those your octopus can learn things. But birds tend to be a pretty good example, and the reason that we tend to look at birds and mammals is that the proportions of their brains are extremely similar to the proportion of brains that we have as primates. So their cognitive abilities tend to be very similar to ours in terms of how they learn things. Okay? In this example, we actually look at the discussion of, well, is this a behavior that is under genetic control, or is it something that's actually learned by the species? So in this case, we're going to look at some lovebirds. Up top, we have the fisher lovebird, okay, in which whenever they make their nesting area, they carry their nesting material in their beaks. And then you have peach-faced lovebirds, in which they actually tuck their nesting materials in their tails. Okay? Two very closely related birds, but yet they have different behaviors as to how they build their nest. Okay? So these different abilities. So what they were questioning is, in terms of nest building, are these behaviors learned, or is it more of a genetic control, and which one is more strongly genetic? Okay? So what they were able to go and do in the lab was, because these two were very closely related, they were able to get them to hybridize. Okay? And as we talked about hybrids before, we said, well, you know, most of the time in nature you don't see that many hybrids. It's usually in the domestication setting that we kind of cause hybridization. Again, not to say that hybridization doesn't occur in the wild, but it's kind of a rare thing. We don't see it very often. So what they were able to do was take these birds in the lab, get them to hybridize, and say, okay, well, what do their offspring do? How do their offspring, how do their offspring build these nests? Do they tuck it? Do they put it in their mouths? And what they found was that the hybrids would try to tuck like the peach-faced lovebirds would. But unfortunately, they tucked it incorrectly. So these poor little birds, I kind of feel bad for them. For 3 years, they would pick up this little nesting material, they would go tuck it in their tail, and then they'd start to fly off. And when they did, it would fall out. So they'd have to stop, pick it back up, put it back in their tail, start to fly off, and it would fall out. They were not doing it correctly. It took them about 3 years, these poor birds, 3 years, they finally learned and modified their behavior that, okay, we can't tuck it in our tail anymore. We're just going to keep it in our beak. But here's the catch to this. Every time they picked up a nesting material, they would turn as if they were going to tuck it. And it's like a little light went off, and they're like, oh, wait, no, I can't do that. And then fly off and go start building a nest. They'll come back in another piece of grass and go, I can't do it. And they would just kind of fly off. So they modified their behavior, even though it took a very long time for them to do that, 3 years. That told the scientists, though, that tucking was under very strong genetic control. They had not been taught that, but that's their instinct. And we call that innate behavior. Okay? Innate behavior is that it's developmentally fixed and under a very strong genetic influence. The same way that when we talked about spiders in the last unit, the spiders, they don't sit there and watch their mama spider build a nest. They know how to build a nest from day one. Okay? It's under a very strong genetic control. Okay? Now, with this being said, you might have heard the old saying, nature versus nurture. I really hate that saying, because when you hear something versus something else, it implies that it's either or, and that's not the case. The case is there's usually a genetic component and there's usually a learning component to that. Some behaviors way more genetic than others. Some behaviors way more learning than even genetic. Okay, but there's always kind of these underlying behaviors. For example, you can look in humans, for example, and see that there are people that are risk takers and those that are not risk takers, that are very conservative. And if you look, a lot of it has to do with their genetics. It has to do with the amount of serotonin and dopamine that we produce in our brains as to whether we tend to go jump out of planes or people that are afraid of tall buildings. It's this kind of risk-taking that does have this genetic component. So when you hear something like innate behavior, it doesn't mean that behavior cannot be changed, though. we've identified many genes in, say, humans in which, you have a gene for alcoholism, for addiction. Does that mean you're going to be an addict or an alcoholic? No. Does it mean you're susceptible potentially to them? Sure. There's genes that have identified for cardiovascular disease. Does that mean that you're going to get it? No. Or breast cancer? No. You're at a higher risk, but that does not mean that those things are going to affect you. Okay? The same way with some of these behaviors, it doesn't necessarily mean that you're going to follow those behaviors. Do you guys know who Eli Roth is? He did Cabin in the Woods, Cabin Fever, the movie Cabin Fever and Hostel. Okay, really kind of a weird looking. He makes some crazy, scary kind of films. There's this show that he was investigating, like psychotic killers, like real killers that did some of the craziest things you would ever think of. And they did all this genetic analysis on them, and they found certain genes, certain markers that all of these guys had in common. And what it was basically discussing was that these individuals didn't have empathy. Like, this affected their behavior of being empathetic, if that's the correct word, to people, which is why they could do some of these things that nobody else in their right mind would ever think of doing. And he asked the guy the question, he goes, well, what about somebody like me? Like, I have all of these crazy thoughts just walking down the street. Like, oh, what would happen if this dude walked out from this car and got hit by these two? Like, because I really have these kind of bizarre thoughts sometimes. And they ran an analysis, and what they found was he also had some of these same markers in place that these serial psychotic killers had, but he had other ones in place in which he could kind of be empathetic at will. Like, kind of, they talk about the psychology of it, that, well, you choose not to do that, because of, whatever reasons. Again, we don't know everything about that. But it was really interesting to see that, even though he was kind of known for his really far out films, that, yeah, he kind of had some of these genes in terms of behavior that kind of marked him for stuff like that. So again, it's these things that there's certain things that are built in, but that doesn't mean that they can't be changed over time. And I'll mention humans a little bit later on, because there have been some pretty good studies on that. In this case, we are getting a little bit more closer to us in terms of mammals. This is a really interesting study to show that even one gene, if it's a very strong gene, can have a huge influence on survivability and reproduction. So again, we're going back to natural selection, but we're applying it into a behavioral sense. So what they were able to look at and identify in these rodents was the FOSB allele. And what they found was the presence or absence of that allele, which coded for certain receptors. Okay, it gets a little bit more complicated than that. That if you had these alleles present, you had certain receptors, that you provided very good parental care. And the way they measured this was if the pups were, the little bitty mice, the little pups, were outside, if they placed them over here, how often would the mother go and retrieve those? Okay, that's an indication of parental care. And what they found was if you had this one allele, that about 70% of the time you would continually retrieve your little offspring. So providing parental care. If you did not have it, if you did not have that allele present, the retrieval was around 20% of the time. So if you have these two scenarios, where is fitness the highest?
One.
In the first one, right? So what does that mean for the survival of their offspring?
High survival.
The highest survival, okay? So when these offspring survive and they have offspring, what do you think they're going to do? They're going to have that allele, and they're also going to take care of their offspring. So you can see very quickly how something like this can start changing through natural selection a character. If you have 50% of the population each with these alleles, in the next generation, you're probably only going to find most of these that have that allele, because these individuals probably did not survive. Maybe only a few did, to carry on the allele that is not present, whereas most of these survive, thus passing that allele on in greater proportion.
Is that a mouse?
That is a mouse, yes. So something as very simple as this type of gene that affects a behavior can changes fairly quickly in your populations. Okay. Switching gears a little bit to another type of behavior. This one's kind of interesting because the behavior itself has kind of went through its own evolution as to what we thought it did and what it actually does. We have these things that they call fixed action patterns. And maybe that's not the best name for it, but they've kind of left it as such. And what these fixed action patterns essentially discuss is that there are certain cases in which when a behavior begins, it continues all the way to the end without interruption. Meaning which the organism doesn't just stop in the middle and reset itself, that it goes all the way to the very end. Okay? A sequence of unlearned, innate behaviors that is unchangeable. However, notice I put unchangeable in quotes because we found that that's not quite the case. Okay? It is usually carried to completion. And let me give you an example of where this came from. The gray-legged goose. You can find there's some rare footage online if you can find of this experiment. What animal behavioralists recognized was that this goose, whenever the egg would fall out of the nest or get knocked out, she would go retrieve it. Okay, well there's nothing unnormal about that. That's usual. We saw that with the mice, right? So your offspring fall out of the nest, you go back and retrieve with that increased fitness, yada yada yada. Okay. However, what they noticed was that this behavior, once it began, she would complete it even if the egg was not present. So this is what the female would do. She would go out and she would take her bill and she would start rolling the egg back to her nest. Okay? And then she'd roll it in the nest and sit down. What the researchers found, though, is once she started rolling the egg, if you snuck up there and just took the egg away, she would keep doing it as if there were an egg there, and then she would sit down at the nest. She never realized that the egg was not there. Okay? So they just kept doing this. She would roll it, they would remove the egg, she'd keep doing it. They'd put it back out there, and she's like, the egg's out, and they come out there and roll it again. They'd remove it, and they did this to this poor bird. She's like, man, I just cannot get this egg. But she would do it from beginning to end, right? She would constantly do that. However, after long enough time, just like we saw with the other birds, she started learning, in which she would start rolling it, they would remove it, and she would stop. I'm like, where's my egg? And then restart it over and roll that egg. It took a long time. That would never happen really in nature, that somebody would come out there and just mess with the bird every single year it had eggs and keep removing it to change that behavior. Okay, because that behavior is, you really only need to do it once, maybe twice, and all is well, you're back to your nest and you're good to go. The kind of funny side of that is, because that's a science stimulus, like something that's round and white, the bird would mistake for an egg. They found rocks in their nest before that looks like eggs. They found little balls that were white in the nest, because she would just see it like, oh, it's a white round thing, must be my egg, and roll it back in their nest. Do you remember those old school porcelain doorknobs? They found one of those in there as well. Just because that was close enough to an egg that it was like, oh, well, it looks like an egg, let me roll it back in my nest. So they found all kinds of random stuff in there. But that's an example of this fixed action pattern. Now again, it is something that they continue, and you see this in a lot of other groups, that once it begins, you follow it to completion. Can it be changed? Sure. It just takes a lot of time in order to do that. Okay?
Do humans have anything like that?
I don't know of
That'd be
anything
hilarious.
necessarily like that. Yeah, I'm not really sure.
Maybe that'd be like our OCD people.
Maybe. I've got to check, my door just to make sure it's locked, And again, this is one of those sign stimulus, something that, is an external sensory stimulus that we call a sign stimulus. It's just usually, it looks similar, close enough. So for example, the way I kind of think of a sign stimulus is, if you were driving down the road and there was this red kind of octagonal sign with no words on it, what does that mean? It means to stop, right? So it doesn't have to have words on it, or maybe it's in a different language. We understand what that symbol essentially means. It's kind of the same way with these sign stimuli, that just that red bottom of that fish was enough to trigger that same reaction. Or even if it wasn't another fish, it was something else, okay, that triggered it. Okay. Imprinting is actually a really neat type of behavior. We talk about it in birds, but even a lot of mammals have kind of this imprinting stage. It's not the same, but it is similar. Okay? I think they call it something else. I don't recall the correct term. Imprinting is part learning and part instinct. Okay, it's part of this innate behavior. And in this type of learning, of imprinting, it is generally irreversible. Now this one, you really cannot change. And you've all seen examples of it. Okay? I'll show you a picture. Okay, in imprinting, you have what is called a sensitive period. Okay, usually very early on in the development of this organism. That is the only time that certain behaviors can be learned. And if those behaviors are not learned, they probably will never learn them. Okay? So it's very, very important. Okay? A very, very distinct type of learning. We see this in birds. How many of you have seen pictures in which you have these ducks following around a dog because they think that's their mama? Okay, that is imprinting. Conrad Lorenz, which is this guy in the picture here, he's well known for this because he was able to get a lot of these ducks and geese to imprint on him as their mother. Now, these organisms don't recognize that they're not of the same species. They learn this at a very young age, and they learn certain behaviors. Now, what he was able to do was he taught them how to swim, how to hunt, how to move through the environment. Okay, he acted as if he was the duck's mother, when in all actuality, of course, he's not. But the ducks don't know any difference. They've even done experiments where they have placed a little tennis ball on a record player so that it spun around, and they put ducks in there before and let them follow that around, and they imprinted on the tennis ball thinking that was their mother. So they imprinted on this tennis ball. They were okay. The ducks were fine. They kept it, okay? But the idea is that it's this very limited developmental phase in which they were able to learn hunting, learn how to swim, learn who their mother was, okay? We have a similar imprinting type stage as humans, but it tends to be with language acquisition. It tends to be with social interaction at a very young age. There was a program that was discussing children that did not have kind of very good education very early on. In some cases, they were discussing feral children, which are children that really didn't have any parents. I know that sounds crazy, but there's examples of feral children or children that have been abandoned. And what they found was from like 0 to 9 was kind of our time period. If you did not acquire language or social skills past that point, it was very difficult for us as a species to pick it up later on. So for example, one of these kids, whenever they were 4 or 5 or something like that, they were unfortunately abandoned by their parents. They didn't get a lot of education or social time. And by the time they were 16, they really couldn't speak very well. They could say words and maybe a phrase and point at things, but they couldn't carry on a conversation the way that we do now, because that language acquisition really needed to occur at certain points when their brain was developing. So that's kind of the exact same thing that we see here in these birds, is that they're able to learn these things very, very at a very, very young age. Now, where we see this a lot is in conservation, because we have to be very, very cautious of our interactions with birds. For example, cranes. If you look down here at this picture, what you find is this is a very young crane. He has a little hand puppet on there in order to feed it. And that hand puppet has all the right signatures of the correct species so that it imprints on the right species of bird. Well, you want that. Before we kind of got into this imprinting, what they were doing was, it's okay, look, here's a bunch of birds that are in conservation status. We'll put them with these other species of cranes, and they'll learn how to fish, and they'll learn migratory routes and all this good stuff. And they did. But the problem was they imprinted on the wrong species, so then when it came time to mate, they couldn't. So these poor birds that didn't have anybody to imprint on, they imprinted on the wrong species. So when they're trying to do their little mating dance and mating calls, the ladies are like, I don't know what you're saying. It's a foreign language to them. So they never mated. So now these populations continue to dwindle because they imprinted on the wrong species. So now, if you watch kind of some of your nature shows, you'll actually see that they have hand puppets. If you notice, his face is covered. Because you don't want birds imprinting on humans, because as they fly, where are they going to decide to land? Around humans. And you don't want to walk in your backyard and then a whole flock of these cranes just land back there expecting you to feed them. That's not going to work, okay? So they do use these hand puppets. They'll cover their face so that these birds don't imprint on them.
But as much as we don't want to hurt the ducks, wouldn't it be beneficial to other species to get the little tiny offspring to imprint on them so that later it could become food?
I think the cost of doing that is way more than the benefit.
Oh, okay.
It would take way more energy to do that, yeah. That would be very difficult to do.
Oh, okay.
But, I mean, we do see that imprinting occurring, okay, but of course, this dog is giving protection to those offspring as well. So there's more cost associated with it. Here's Conrad Lorenz again, and here's some more of his imprinted geese, following him to feed. He's very well known for this behavior. Now, why we see this in nature in terms of imprinting instead of just kind of looking at this, is that if you're these birds and you follow your correct parents, you're going to get that parental care, you're going to learn the necessary skills to survive, and ultimately, you have a greater chance of surviving than those that do not follow their mother, okay? Because your mother will provide lots and lots of parental care for your survivability, okay? So next time you see some of these cutesy photos, just realize, oh, there's some imprinting going on. And you've probably seen, like dogs and tigers hanging out and all this stuff, because they grew up at a very young age, they imprinted on one another. Now, that imprinting is a little bit different than, of course, bird imprinting. The movie Fly Away Home, you guys seen that? It's an older film. But again, kind of the story is part of that imprinting and teaching these birds, their migratory routes. So if you see these ultralights, you'll notice that he's also still kind of dressed out in his white garb, face covered, okay, to get these guys to go to their migratory routes. And you just have to teach these guys probably once, and they'll follow these routes year after year. Okay. Learning of song is another example. It can fit into your imprinting based on what these guys are hearing. And what's really interesting about this experiment is that it does show that there's a lot of learning, but there's still a genetic component to it. So what the researchers asked was, in terms of song learning in birds, which is a vocalization, which is essentially speech, where do you learn it from? That's like for us, we have innate capability of wanting to speak. We make sound at a very young age, but our language is acquired later on. That's very much learning, which is why there's different languages. If you grew up in another country, you may not be speaking English. So what they did is they said, okay, well, let's take 3 of our groups of birds, and let's kind of design this experiment in order to test what components, if any, are under genetic control in terms of learning songs. So they put one group all by themselves, these little bitty chicks, right when they hatch. They put them all by themselves, no birds around, no sound. They tried to see what happened. Then they placed a group of birds by themselves, but they played tapes of songs. And then they did another group in which they actually put the actual bird in there that would sing, and they wanted to see what the outcomes were. So with the birds that did not hear a song, they still sung. Even though they had never heard a song before, they still were chirping. But it was a very incomplete song. It wasn't quite fully formed song. The way I kind of think of it is, you know, a new song comes on the radio and everybody's like, oh, I love this song. And you can sing the chorus, you know the words, and then you get to the verse and you're like, you just kind of hum it because you have no idea what they're even saying, but you know the chorus and you rock out on that one. It's kind of like that. But these birds knew little bits and pieces of this song that they would try to sing it, but it wasn't very well developed. So that told them, well, there's something genetic to this that they want to sing. They have kind of a song, but it's very, very incomplete. Okay? But whether they heard a tape of the song or the adult bird, whether it was the same species that they were or even a different species, they learned that song. Okay? So again, you do have the potential for one species of birds to learn the song of another, but usually, because they're in the nest and the mother's taking care of them, they hear their mother and father's song, and that's where they learn it from. They want to sing, they just listen, and they hear it from their own parents. But in this experiment, it showed, well, even if you put a different parent with them, they would learn that song in these types of songbirds. Okay? Not all birds do that, some are a little bit different. Okay? So it was a really cool example of showing, again, that genetic component and then that learning component in times of a language acquisition. And our nice little picture here, what you see on the left is beforehand, okay? In which if you have a dog and it finds some food, it's going to begin to salivate. That is an unconditioned response. Does anybody have that?
No, it salivates because it's hungry.
No, you yourself. Do you have an unconditional response? You've been watching TV and a Wendy's commercial comes on, or McDonald's, or maybe not McDonald's, something comes on and you're like, man, that looks really good, and your mouth starts to water. For me, my mouth is watering right now. Pickled jalapeno peppers. I don't know why, but for me, like, I'm salivating right now. It's crazy. I can just think about it, and my mouth is like, okay, let's go. I'm ready. I'm salivating because that's the first part of digestion. Let's do this. Sometimes you can smell things, you know, maybe freshly baked chocolate chip cookies, and you're like, oh, that sounds good. And it's what we call mouth watering, because your body is getting this stimulus externally, and that's eliciting this reaction. That's an unconditioned response. Again, like I said, I don't know why jalapeno peppers, but sometimes Wendy's commercials will get me, or Burger King. I'll be flipping through, and I'm like, oh yeah, the Baconator looks delicious. And I'm like, it's probably not the best thing for me, but it looks really, really good, right? That's how advertising works. They get me every time. That is this unconditional response, okay? So for a pet, if you have a dog or even a cat, they will salivate at the sight of food. That is an unconditional response. You did not tell them, hey, you need to salivate. That's just something that we do, and that is unconditioned. And the food is an unconditioned stimuli, okay? You put food up there, they get hungry, they're gonna go eat, okay? Same with any of us. So what Pavlov was questioning was, well, I understand that there is this stimulus to give a result. Can I change that stimulus to something completely different or arbitrary, but yet still get the exact same result? So he was trying to take the unconditioned stimulus and associate it with something else so that you can get a different stimulus, but yet get the same effect. So, as you guys correctly told me, what he began doing was whenever he would feed the dog, he would also ring the bell at the same time. So now the dog began to associate bell, food, I get to eat. Okay? And he did that for a while until eventually the food was never there. He would ring the bell and the dog would salivate, even though that stimulus of food is nowhere in sight. He doesn't smell it, he doesn't see it, nothing, okay? So that now you've got the stimulus that is arbitrary, that you now have, even though it's a conditioned response to a conditioned stimulus, it's the exact same response as the unconditioned variety, okay? So you ring the bell, and you get salivation, okay? I don't know if you have...
They did it on The Office, too.
And that's what I'm
Oh, really?
Yeah. Well, maybe not. It's not wanting to let me play it.
It doesn't want to be a thing?
Guess not. Sometimes they start moving links around and it really messes up my PowerPoints. Or, I think my dog has me trained more than anything. When we got our dog, we trained her to ring a bell when she needed to go outside to go to the bathroom. So now, she needs to go outside, she'll ring the bell, and we'll go let her out. The problem is, I've been trained now because I'll be sitting on the couch watching TV and I'll hear the bell, and I'll just get up like a zombie, open the door, let her out, go sit down, and my wife will come down. Did you let the dog out? I guess. I don't remember. So now I'm trained that when I hear this bell, I just get up automatically without even thinking. I just kind of go open the door and let the dog out. So I've been trained, even though I was trying to train my own dog. Where you are probably the most familiar with associative learning is the other type of associative learning, and that is your operant conditioning. Now, in this case, you're actually associating with the organism's own behavior. Okay? Whether it's a good association or a bad association. Okay? So in which your animal learns to associate one of its own behaviors with a positive or a negative. So of course in the top picture, curiosity did not pay off for this little guy. So that behavior has been disciplined, at least when it comes to porcupines. Right? So this little guy has learned that things that look like a porcupine, I probably will not mess with again. And this is the type of behavior that we mentioned before when we talked about toxic plants and we talked about toxic animals. A bird or something, a mammal that's eating something that's toxic will get sick from it, and you will learn not to eat that anymore because you kept getting sick, which is why birds, you will eat 2 or 3 monarch butterflies and you're pretty much done after that. Now again, some birds can tolerate that and eat them left and right, but some birds can't. It makes them very, very sick. Something that I found kind of fascinating, again, kind of as in humans. Have you ever gotten food poisoning, gotten sick from a restaurant, and you just can't go back there? Even if it's a different one, in a different state, you just can't go back to that one restaurant. There's a Sonic that we went to, we got sick, and now my wife is like, I don't want to go to that Sonic. I'll go to another Sonic, but I just can't go to that one. Even though it's probably fine, it was just that one time that we got sick from whatever. We kind of have this idea in our brains that we've associated something bad with it, and we're going to stay away from it. Okay? Again, it's that kind of associative learning. We know this as trial and error learning. Now, where we know this the best is dog training. Okay? If you've got a pet dog, not a cat, cats really, you can kind of do it with cats. You can teach cats to use the litter box. You can teach cats to use the potty, the toilet. You just kind of trick them up there and get them to use it. It's kind of creepy. To open the door and you're like, oh, there's a cat sitting in the toilet. Okay. But you can train pigs, you can train rabbits, you can train dogs, and a lot of it is this associative type learning. If you've ever watched kind of like the dog whisperer or something like that, a lot. If you get into it, you're like, okay, there is a lot of associative learning because a dog has natural tendencies, and you have to be able to identify those tendencies and either reward or punish them. Okay, that's just like training your dog to sit. Okay, if you're talking to your dog and you're like saying sit, sit, does it know what you're saying? No. You could be speaking in German, you could be speaking in Spanish, English. It doesn't matter to it. Okay, there is a classical part of this, but you're saying sit. Your dog will eventually just be like, I don't know what you're saying, and get bored with you. And what does the dog do? It just sits down. That's a natural tendency for a dog. Like, I don't know what you want, I sit down. And when that occurs, you reward the dog. Oh, here's a treat. Good boy or good girl, And now the dog's up again. It's like, okay, what did I do? Great. How do I get another treat? And then he gets bored with you again, and he sits down, and you give another treat. And the dog, aha, I'm sitting down, I get a treat. Whenever we first started training my dog, sit, okay, good. We come home, run up to me, just sit down automatically. Like, okay, I get a treat. I sat down, right? because they've not associated, okay, every time I get a treat every time I sit down. Even though I'm not telling the dog to sit down, the dog's like, where's my treat? Doesn't work that way, right? So what you've done is there's a natural tendency for your dog to sit down, but you are rewarding that behavior with a treat. And the arbitrary part is what you're saying, okay? A vocalization, whatever word. You could say blue and get the dog to sit down because it associates that word now with the behavior. So there's kind of two aspects of that. One's associative, one is operant and one is classical. If you look at canine units, what language are they usually taught? German, right? They're usually taught in German. So you can yell at them all day in English, they don't know what you're talking about, okay? Because they don't associate with those words certain behaviors, okay? Which is why dogs, are in all languages know how to sit because there's all different words. They associate it differently. You don't even have to use words. You can do hand signals, okay? To make your dogs do things.
There's a deaf dog that
Yeah, they learn
trained
signals.
it, and then they took it to the deaf kids, and all the deaf kids could communicate with the dog and
Right.
do tricks.
Yeah, because it's association. They learn certain behaviors, but then they associate this kind of arbitrary. So a lot of your dog training that you've done, most of it is your operant conditioning, that a dog will naturally do these things. A dog will roll over all by itself without you saying anything, or just laying on its back. And we say, oh, it's playing dead. My dog doesn't know to play dead, but it plays dead all the time. Just lays there and just relaxes for a bit, right? So a lot of this we're actually very familiar with, and in the bottom right is, I pulled off of one of the dog training websites, the 4 quadrants of operant conditioning, and it's talking about positive reinforcement, negative reinforcement, positive punishment, negative reinforcement, all these different aspects of that dog training, because dogs can associate with that. I've seen some problems with this though. In some people, where you get a new pet and you leave them for the day, you go to work, and what does the dog do? Chews up everything. The dog is going through anxiety because you're gone. You get home kind of happy to see your dog, but then you're very upset that the house is a wreck. The problem is you can't discipline your dog right then and there because the dog will not associate that disciplinary action to what they did 6 hours ago. What do they end up associating that discipline with?
When you get
Coming
home,
home.
once you came home.
So what I've seen before is when people get home, they open the door, what's the dog do? Runs. It gets out of there. Because the dog associates, every time you get home, I get in trouble. But we as people think, you know what you did, you know you did something wrong, that's why you're running away. No, they just know every time that you come home, they get disciplined, they get in trouble. So they're not associating the mess that they made in the corner that they did 6 hours ago, they're associating with you coming in the door. And I've seen that unfortunately in a couple people where you have to kind of catch them in the act of doing that for that association to actually occur. There was a really cool thing on PBS where they wanted to look and see if dogs could pick up on emotions from humans, and the experiment was actually pretty simple, pretty easy. They had the researcher sitting in the room with the dog, and the owner would bring their dog and say, okay, sit, stay, and then they would put a treat on the floor, and the owner would walk out. And the dog would just sit there and look at it. It's like, man, I'm really, really hungry. That treat looks good. And the owner would come back in, it's like, okay, good dog, and then give them the treat. So the dog was rewarded. Very good. So then, they did it again, but then as the owner walked out, the researcher took the treat and just kind of hit it. The dog kind of looked at him like, what are you doing? And then the owner came back in and was like, where's that treat at? Did you eat the treat? And the dog cowered. It was like the dog felt guilty even though the dog didn't do anything wrong. So it was picking up on kind of the emotions of us. That's how tied we are. So you have to be really cautious because what we kind of place in terms of emotions on these animals is not really the emotions they're feeding off of ours. So it's really, really kind of interesting when you look at how animals are associating certain behaviors. Like I said, operant conditions are one that we know the most. Okay. Sorry. I like the little section. It's fine. Habituation, again, something that we probably do quite a bit. You might not recognize it though. Habituation, the loss of responsiveness to a stimuli, that doesn't really cause anything negative, but it doesn't cause anything positive either. My best example, I think, is like deer on a highway. You're driving down the road 7 miles an hour, and you pass deer. What do most deer do? Just stay right there. It's like, oh, there's another car. There's another car. What happens if you start slowing down?
Like pop your head down the window.
They get a little bit more interested, and if you stop, they're gone. You know, if you drive 45 or I-10, you'll see deer all along those highways, right next to the highway. They're there for hours. All these cars are passing by. They're habituated to that just constant flow until something happens. Somebody slows down, honks, or something like that. That's why I get scared. I'm like, I don't want to honk because they may not be used to that, and then they're going to scatter and then jump right in front of my car. Okay? Sometimes the best thing to do is just keep going. Okay? The example that they look here is like a hydra. Okay? What they were able to do was a hydra, they could touch it and it would retract. It would try to move out of the way. But after a while, they kept touching it and it stopped moving. Because that stimulus, it didn't hurt them, it didn't help them, so they just lost responsiveness. They become habituated to it. Okay? The same way that maybe you can leave the TV on when you're sleeping, it doesn't bother you, you're habituated to it. Or maybe you live next to a noisy neighbor, or you're used to that sound. Okay? But with this hydra, they kept touching it, so it lost responsiveness, but they reset it. They were touching it, and then the next time they touched it, they applied electrical shock. And that was a negative. And then the next time they touched it, no shock, nothing, just regular, they touched it, and it started retracting again. And it would retract, and retract, and retract, until eventually it became habituated one more time. And then you could apply a shock, and it would move, and it would start moving more, until it became habituated again. Okay? So it's this thing where you lose kind of responsiveness to this stimuli. You know, I could probably come tap you on the shoulder. It'd probably be annoying for the first hour, but eventually, if it wasn't hurting you, you'd probably kind of forget about it. You know, you just get used to that. Yeah, okay. Okay. How do organisms navigate? How do they move through the environment? Okay. How are they able to use the ability of learning in order to navigate? This is kind of a big question, and it's different for a lot of animals. You know, when you look at certain birds, they're looking at certain crystalline structures that help them orient towards the poles. You're looking at dung beetles, which actually use the Milky Way galaxy in the sky as a navigation tool, which is really kind of crazy. It's a neat experiment. They took 2 groups of dung beetles, one just a normal dung beetle, and one they put caps on them so they couldn't see the sky, and watched how they navigate. And of course, the one with hats that couldn't see the sky, the Milky Way, they were all over the place. They didn't know which way to go. Okay? But the ones that could see the sky said, oh, that's north. And there they went. So navigation is really kind of this important tool to learn because it gets you from point A to point B. It allows you to find your way home. And there's many different levels of this type of learning. Spatial learning is one that's fairly simple. Okay? In this case, you do modify your behavior learning, okay, based on experience, but you do it with the spatial structure of your environment. And one of the aspects of this is what we call landmarks, using landmarks for navigation. So if I were to blindfold you and drop you somewhere, and the first thing you saw when you took off your blindfold was the Eiffel Tower, where might you be? Paris. Vegas. Or?
A gift shop.
Maybe a gift shop. You could do that. Okay. Paris or Vegas are kind of 2 of the big ones. Paris, Texas. Yeah, we got a little Eiffel Tower there too. Of course, they put a big cowboy hat on it, right? If I were to do the same thing and you saw the Statue of Liberty, where might you be? New York. Or Vegas. Or? New York, Texas.
Another gift shop.
France.
Oh, yes.
They've got a little one there. Okay, not a big one, right? But that's a landmark. You have a pretty good idea of where you're at. You know, for me, driving up 45, you turn around the corner, and in the distance you can see the big Sam Houston statue, the big ghost of Sam Houston. I know that, okay, I'm really close to Huntsville because you can see that statue. That's a landmark. So a lot of organisms use their environments in order to navigate using these landmarks. In this experiment that they did up top here, what they were able to do was you have this ground burrowing wasp, and they started placing all these pine cones around it, and that was easy for this wasp to navigate toward because this is a nice circle of pine cones. So the wasp flew out one day, and the researchers went over it, and they shifted that circle to another location next to the nest, and guess where the wasp flew? To the circle, and started looking for its nest, and it couldn't find it. Probably got pretty angry because it's like, where'd my nest go? That organism had used that as a landmark. Now, what it didn't recognize was that landmark had shifted in space. Okay, that's a little bit different. That's a different type of learning because it was focusing on 1 to 2 items. That is something a little bit more that we have to look at in just a second. So they can follow these things, and they will sometimes use pheromones. They'll try to pick up on scents to follow things. So there's more to it than that. But that is kind of their first go-to in terms of navigation, is certain landmarks. And as those landmarks move, okay, so do those insects through the environment. That's been seen with bees, for example. It's been seen with a lot of insects, that they'll make the rounds based on certain landmarks. And if you move those landmarks, you change the way that they move in the environment. Migration, we tend to see with birds, but you do see it also with insects, such as butterflies that migrate. The monarchs migrate all the way to Mexico. I think that was one of the shows we watched, and then they come all the way back. In this picture, it goes to show that migration, there is a little bit of a genetic component, because migration, all these birds, there's a want, they get really restless, right? They've got to move. But sometimes they don't know exactly which direction to go. That's the learned part. So what they were able to